Calculating the stress beneath a concentrically loaded foundation is a fairly straightforward task. It's simply stress is equal to load over area, or symbolically Q is equal to V divided by B multiplied by L. It is assumed that this gives a uniform stress distribution beneath the foundation as shown. However, many foundations in engineering practice also include lateral loads. For example, wind loading on buildings or earth pressures in the case of retaining walls. The presence of lateral loads changes the distribution of stress beneath the foundation from one of uniform stress to a non-uniform stress distribution as shown. How we calculate these stress distributions is a little more involved than for a concentrically loaded foundation. The vertical and horizontal loads combine to give a resultant force which is inclined at some angle to the vertical. Hence, this inclined force will intersect the base of the foundation some distance away from the center line. This distance is known as the eccentricity E. In some cases, we know the eccentricity of the load. For example, when there has been a setting out error on site and the column ends up being positioned away from the centroid of the foundation as shown. In such cases, the calculation of stress beneath the foundation can be easily determined using Meyerhof's effective foundation method. Meyerhof modelled the eccentrically loaded foundation by assuming the vertical load now acts at the centroid of a new reduced foundation size, known as the effective foundation. Here's how it works for a column positioned with an eccentricity EB along the B direction only. We can see the width of half the effective footing is B over 2 minus EB. Therefore, the width of the full footing is twice this, or B dash, the new effective width, is equal to B minus 2 times EB. As the vertical load acts at the centroid of the effective foundation, the resultant stress represents an average uniform stress beneath the effective foundation. Similarly, when the load is eccentric in the L dimension as shown here, the effective L dimension now becomes L minus 2 times EL, where EL is the eccentricity in the L direction. However, others suggest for two-way eccentricity, that is, in both the B and L directions, the determination of the effective area becomes quite complex and is often dealt with by the use of charts such as the one shown here. The second case mentioned involving eccentric loading is for a retaining wall. In this case, the point of application of the eccentric load, that is, the position of the resultant load with respect to the center line of the foundation, is unknown and must be calculated. I will demonstrate how to do this in the next video.